Now we have to relate analog and digital filter poles in bilinear transformation like we did for IIT. The mapping of S domain function here means transfer function. Z domain function by bilinear transformation is a 1-to-1 mapping that is for every point in Z plane there is exactly one corresponding point in S plane and vice versa. The transformation is accomplished by S equal to 2 by T into 1 minus Z raised to minus 1 upon 1 plus Z raised to minus 1. Let us call this as equation 7. Seven can be simplified to T by 2 into S equal to Z minus 1 upon Z plus 1. Let us call this as equation 8. Also, it can be simplified to obtain the value of Z. Z equal to 1 plus T by 2 into S upon 1 minus t by 2 into s. Let us call this as equation 9. In equation 9, if S is a point in S plane, then Z is corresponding point in Z plane. Let Si equal to sigma I plus j omega I on substituting Si equal to sigma I plus j omega I in equation 9, we get Zeta equal to 1 plus t by 2 into the bracket sigma I plus j omega I divided by 1 minus t by 2 into sigma I plus j omega I. We can separate here real terms and imaginary terms. 1 plus capital T by 2 sigma I plus j omega I into capital T by 2 divided by 1 minus capital T by 2 sigma I plus j omega I into capital T by 2. Now we will find what is the magnitude of this Zi. We know that the magnitude of complex number is square of real part plus square of imaginary part under the root. So, magnitude of Zi is real part square plus imaginary part square in numerator and denominator whole raised to half. Whole raised to half means what? Square root. And let us call this as equation 11. From equation 11, the following observations can be made. First one, if sigma I is less than 0, sigma I is less than 0, it means that sigma I is negative. If sigma I is negative, on S plane we will be having pole on LHS. What I get if I substitute for sigma I as negative in the expression for magnitude of Zi? By substituting for sigma I negative here and here, we get the magnitude of Zi less than 1. Then the point sigma I plus j omega I lie on the LHS of S plane. So in Zi, when I get numerator less than denominator under the root, Zi value will be less than 1. Zi magnitude is nothing but radius of the circle in Z plane, but that is going to be less than 1, which means the pole in Z plane corresponding to the pole in S plane for sigma I less than 0 is going to map within the unit circle. Within the unit circle. In this case, Zi is less than 1, hence the corresponding point in Z plane will lie inside the unit circle in Z plane. Second observation, if sigma I equal to 0, then the point Si equal to sigma I plus j omega I lie on the imaginary axis in the S plane. Now if we look at magnitude of Zi, for sigma I equal to 0 in numerator and denominator, we get 1 square plus omega I capital T by 2 whole square and 1 square plus omega I into capital T by 2 whole square. So the magnitude of Zi will become equal to 1. In other words, the pole that lies on the imaginary axis in S plane, that will be mapped to a pole on the unit circle in Z plane. So I'll write here in this case Zi becomes equal to 1, hence the corresponding point in Z plane will lie on the unit circle. In Z plane. If sigma I is greater than 0, that is sigma I is positive, then the point Si equal to sigma I plus j omega I lie on the RHS of S plane. Please remember, when I say LHS and RHS, it is with respect to imaginary axis. In this case, magnitude of Zi will become more than 1. Hence, the corresponding point in Z plane will lie outside the unit circle in Z plane. So based on this discussion, we can say that an stable analog filter is transformed into a stable digital filter by bilinear transformation. Students, now we will take the relationship between analog and digital frequencies in bilinear transformation. Let S equal to j omega be points on imaginary axis and the corresponding points on the z plane on unit circle are given by z equal to e raised to j omega. We know that S is equal to 2 by capital T into 1 minus z raised to minus 1 upon 1 plus z raised to minus 1. Put S equal to j omega and z equal to e raised to j omega in equation 12. Therefore, we get j omega equal to 2 by capital T into the bracket 1 minus e raised to minus j omega upon 1 plus e raised to minus j omega. That is equal to 2 by t into the bracket. I will write 1 as e raised to 0. We know that a raised to 0 is equal to 1, like that e raised to 0 is also equal to 1. This 0 I will write as j omega by 2 minus j omega by 2 minus e raised to minus j omega as it is. Similarly, in denominator, e raised to j omega by 2 minus j omega by 2 plus e raised to j omega. Two by t into the bracket. Now I will take e raised to j omega by 2 and e raised to minus j omega by 2 separately by using laws of exponents. That is e raised to j omega by 2 into e raised to minus j omega by 2 minus e raised to minus j omega by e raised to j omega by 2 into e raised to minus j omega by 2 plus e raised to j omega. Now we can take common outside e raised to minus j omega by 2. Taking common outside from both numerator and denominator, e raised to minus j omega by 2, we get inside the bracket e raised to j omega by 2 minus e raised to minus j omega by 2, and in the denominator we get e raised to j omega by 2 plus e raised to minus j omega by 2. Now, using sin theta equal to e raised to j theta minus e raised to minus j theta by 2j and cos theta equal to e raised to j theta plus e raised to minus j theta by 2, we can write numerator and denominator here as sin of omega by 2 into 2j by cos of omega by 2 into 2. E raised to minus j omega by 2, e raised to minus j omega by 2 will cancel. We can cancel 2 and 2 here to get j omega equal to 2 by capital T into j sin of omega by 2 into cos of omega by 2. Now j and j will cancel. We get analog frequency omega is equal to 2 by t into sin by cos, we know that tan, therefore 2 by t into tan of omega by 2 we get. So what is the relation between analog frequency and digital frequency? The relation between analog frequency and digital frequency is analog frequency is equal to 2 by t, that is sampling time, into tan of digital frequency by 2. Or we can write for digital frequency. T into omega by 2, transferring this 2 by t on LHS. T into omega by 2, transferring 2 by capital T to the LHS. We get tan of omega by 2. Taking tan inverse on both sides, we get tan inverse of t omega by 2 is equal to omega by 2, or digital frequency omega is equal to 2 into tan inverse of omega into capital T by 2. Now let us call this as equation 13 here, and this as equation 14. The equation (14) can be used to estimate the digital frequency for a given analog frequency omega. The equation (13) can be used to calculate the analog frequency for a given digital frequency. From the above analysis, it is evident that the analog frequency omega and digital frequency omega has a non-linear relationship because the entire negative imaginary axis in the S plane that is from omega equal to minus infinity to 0 is mapped into the lower half of unit circle in Z plane. That is from omega equal to minus pi to 0 and the entire positive imaginary axis in the S plane that is from omega equal to 0 to plus infinity is mapped into the upper half unit circle in Z plane. That is from omega equal to 0 to plus pi. This non-linear mapping introduces distortion in the frequency axis. Which is called frequency warping. Dear students, I advise all of you to verify the above said statements by taking different values for capital omega, that is analog frequency, as given in brackets, and by obtaining corresponding digital frequency, that is small omega. Now in this graph you can see mapping between analog frequency and digital frequency for IIT and BLT. Dear students, I stop the class here and continue in next class. Thank you.